today. Pretty dense lecture. So sit tight. If you have any questions, raise your hands. I think there will be some time for questions. There's like 7 subsections of this lecture. So definitely between every new subsection, go deep into the questions. If anything confuses you, ask around. We should have hopefully plenty of time to cover that, especially because we'll be doing detailed stuff today. Like we had some philosophy and direction lectures yesterday. Today we are actually explaining how it works right now, how Polkadot operates. So maybe a quick introduction of myself. I'm Maciej. I'm working in the Parachain protocol team. This is that team that's building the Polkadot runtime, the runtime that aggregates all the parachains, that takes in all those like WASM blocks and creates the final result, the relay chain that aggregates the computation and helps shard execution and data. Okay, sharding. So the first thing is the core pillar of Polkadot where sharding is actually implemented is the parachains protocol down there at the bottom. We are covering the data sharding and execution sharding in parachains protocol. There are a few other important pillars as well, which is NPOS and governance. With governance, hopefully some of you are at least a bit aware of what role it actually has. The main thing it does for us is it parameterizes the game we'll be playing. And that game is the parachains protocol. This is the runtime of Polkadot. This is the core logic of how parachains come together. And NPOS is quite simple for our case. We'll be just taking as a given. All it gives us the players playing our game in the parachain consensus. It gives us the active validators, the 300 Polkadot active validators that will be playing our game. And let's outline why we even go through all the trouble, like what's the point of sharding? And sharding, you could say, is an answer, at least our answer, to scalability. And you could argue it's solving scalability, but it's a bit of a simplification. Generally speaking, there are no real solutions, there are only trade-offs. And in this case, the sharding is also a bit of a trade-off. So we'll be exploring what do we sacrifice to achieve that, how do we get to that result, and how do we optimize for scalability without losing security. So why is there even a scalability issue in blockchain? Like we all heard they supposedly don't scale. So in short, what causes them to scale poorly? Any simple answer why blockchains scale poorly? Any hands? Do we have a mic?
Hey, maybe because they share a global state.
Yeah, sharing global state is definitely one of the issues. It will be connected, it will be partially solved by data sharding, but there's also the aspect of not only they share the state, a lot of the execution also has to be shared. We compute the same thing multiple times. And well, computing the same thing multiple times is not particularly efficient. So everyone checking everything is just sacrificing a huge amount of scalability for security. And this is what Bitcoin does. In Bitcoin, everyone checks how the blocks goes through. Yeah, it's super safe, it's super simple, but it just doesn't work. It's not future-proof. It doesn't scale. It introduces so much unnecessary work that it stops us from scaling. So a small analogy, like imagine having a startup company with 3 employees and you all make some like handcrafted bags or some kind of an item. And at the end of the day, you all meet up, share your products and check for any defects. If there is any problem in any of the items, like it will be caught if maybe one of the employees was lazy, they didn't do a good job. At the end of the day, you will figure it out and say, oh, you didn't do a good job, we need to take it away from production. And this is how Bitcoin was working when it was small. Everyone was checking everything. Everything was good because the network was small. It was manageable. But imagine the company just grows to 100 people. And what? So if we have 100 employees, then at the end of the day, we have so many bags to check. And everyone has to check every single bag. Like this just no longer works. Okay, so wait, is that it? Like it doesn't scale. We close the company. Like making handcrafted bags just is not a thing. That's it. Like obviously no. Like we solve it by doing something, and we'll be exploring what that something can be. We need to change our ways. We need to introduce new levels of abstraction and responsibility management. So maybe people working in the company really dislike checking for defects and would rather be making those bags. So bug makers simply take turns checking for defects. Some of them, if they spot a defect, they can escalate the issue. And only if there is this escalation, then the other bug checkers will actually go and look at that bug, and this specific person that produced it will be held accountable. And this introduces this idea of escalation. And escalation, I think, is one of the most important principles when it comes to execution, to sharded execution in Polkadot. We'll be using that idea a lot, and we'll be building to how we use it. And the escalation is like this, hey, everyone, check this out. We have a problem here. Come and check it out. Like, this is the whistleblowing of corporations. This is what we do. And like when big corporations like Google, Microsoft, they do something not according to law, but it's very hard to figure out. If there's like a single whistleblower that can escalate the issue, that is enough. Even for the most corrupt corporation, if there's like a single brave person to whistleblow, that's it. Like, it's all we need. So how does it actually relate to Polkadot? So in Polkadot, not all validators check everything. Like, it's just not scalable. But enough of them check that if there is a problem, it can be detected. But the detection only leads to escalation. And the escalation will actually give us the truth. Escalation generally causes everyone to check. It's very expensive to do, but this is the final source of truth. So some of the properties of escalation. Escalation is generally a happy path optimization. So if there are no issues, then there will be no escalations. And remember, escalation means everyone has to come in and check. It's very expensive to do. But if there are no issues, then only a small subset can continue checking, and we never divulge into this huge escalation problem, which is super, super costly. And the happy path optimization is useful because in reality, most blockchain blocks are valid. Like, there are not too many attackers. They happen once in a while, but the vast majority of people and users, simply validators, they produce valid blocks with valid transactions. So happy path optimizations are incredibly helpful. And you can also remember that we had the discussions around optimistic rollups, which are also a type of a happy path optimization. They're a bit more aggressive optimistic optimization that we have. They are going super, super optimistic. We are only going like a bit optimistic. It's like a sweet middle ground between ZK and optimistic rollups. So if there are any issues, due to escalations, everyone will be checking everything, which also means that we temporarily break sharding. Like, sharding is what we are trying to achieve, but it's an optimization for the happy path. We cannot always maintain it. In the end, security is the core goal, and sometimes we have to sacrifice sharding to still maintain security. That means that sometimes we will slow down the whole system to protect security. But we need to maintain some liveness, some block production to still make the blockchain progress. It makes sense because if what we care about is the quality of the bags, looking at the analogy, then we care about the quality of the product. And in blockchain, we care about the security of the block space. Even if we slow down for a bit, like, the most important thing is like this blockchain thing, it should not be attackable. Like, we don't want to succumb to any single attack. So if anything happens, we go into like this protection mode, delegate, escalate, and protect as much as we can, even though we slow down to be as defensive as possible. So now that we have the core principle of sharding, let's look at how it actually manifests in Polkadot, the details of how it happens, and what components actually make it work. So the parachains protocol, which gives us execution sharding and data sharding, but that will be the next lecture, is a combination of five primary protocols, which is collation, backing, availability, approval checking, and disputes. Some of those names hopefully are at least vaguely familiar to you based on the previous lectures. Today we'll be jumping deep into them and actually explaining what they do and how they achieve what they try to achieve. Okay, and there's one important note, like this whole parachain protocol system, it's running asynchronously on multiple threads at the same time. for different parachains. So maybe if you're a validator, you might be importing like collations for one parachain. You might be validating and approval checking for a different parachain. Maybe you're distributing some availability for a totally different one. So it happens at the same time for multiple ones. It's not just like, oh, I'm just backing for this one parachain and do nothing else. Many of those things happen at the same time asynchronously. But we'll be focusing on each step by step so we can actually understand how the path progresses of a single candidate through the system. Okay, so let's look at the first thing, collation. But actually, there's one a bit of an unofficial step before that, which I call assignment. It's not technically a path of a parachain block, but I think it gives us enough context to fully understand the later steps. So to achieve this assignment, we'll be working with a set of active validators. So as I mentioned at the beginning, the parachain protocol is given a set of active validators through the NPOS election. It happens every single 24-hour. We have an NPOS election, which gives us a new set of 300 active validators, and those will be participating in the game of the parachain protocol. And they're like the core players doing everything, all the responsible roles in that system. Others, because there are other validators that are not selected for this set of 300, they are currently sitting on a bench. They might have a chance to join the active validator set next election, so the next 24 hours. And every session, which is 4 hours, we split those validators into small subsets we call backing groups. So generally, each backing group has between 3 and 5 backers. Right now in Polkadot, it's primarily 5 backers per group. So we simply randomly split them into minor groups, and those groups will be playing a crucial role later on in the subsystem. And it happens every 4 hours. And each of those groups that we create here, as a small spoiler, each group will be responsible for a single execution core. There's like a one-to-one mapping from a group to a core. Okay, so this is the big overall picture of like the Polkadot relay chain. It's a lot to consume if you're seeing it for the first time. But the thing we are primarily interested in now is where in this picture do we have our backing groups? So the big pink circle at the center, there's the relay chain. We have a bunch of parachains around, and we have the backing groups here. In here, we know that there's like 3 validators in each backing group. In Polkadot, we have 5, but the logic stays exactly the same. Here, spoiler, we'll have the collators, and this whole like pipeline goes from collators, parachain block, backing group, execution core, relay chain, and we'll be exploring that path. There is one extra thing. The backing groups, the assignments we have, they are rotating around. So probably the best way to explain it is every few blocks. There's a question? Yep, go on.
How much is the stake of each group assignment?
Each validator?
Yeah.
Millions of dots. It's like a huge amount because the validators do not necessarily have their own stake. It's a bit of an NPOS question. They have the stake of their nominators that nominated them. And it can be huge amounts of dot. I can give you the numbers, exact numbers later on because I don't have them at the top of my head, but generally it's huge amounts. I think it's like, it should be around, I think mostly, Polkadot has roughly 50% of DOT being staked actively. And most of that stake should actively be held by those 300 chosen validators. It's like used to nominate them. So you divide 50% of the total cup of Polkadots and distribute it among the 300 validators, and this will give you a number of how much per each one, roughly speaking, but generally a lot. Going back to rotations. So if we have this backing group temporarily like corresponds to this execution core. After a few blocks, what we do is we simply rotate it around. So this group goes to the next execution core. Every few blocks, just rotate it around. It might seem a bit unnecessary now, but it gives us some very nice properties of what if the whole group is malicious? Well, if they would be malicious, they can completely censor a specific parachain, which is not ideal. If we rotate it around, it at least gives some liveness, some uptime to every single parachain. Question?
So the process you're describing is what you said happens every 4 hours?
The process happens every few blocks. What
Every few
happens
blocks.
every 4 hours is creation of those backing groups. So every 4 hours, we will decide partition those validators, those backers differently into those groups of 3 or 5. But every few blocks, we just rotate it around.
Thanks.
And it's all parameterization. Like it can change. It's a type 2 decision. Right now, it takes 4 hours and every few blocks. But you can just have an OpenGov referendum and change it to every 6 hours if you want to. This is just something that works in the current iteration of Polkadot and makes sense for the current state of things, but it can be changed at any point. Okay, and now we can actually go to collation, which is the main first official step of the protocol. And going back to the same image. So collators. Collators, you heard the name. Collators, shown by those white dots around here, they are not validators. We had this active set of 300 validators. Those nodes are not those. It's a separate class, separate entity outside of the validator set. They are running parachain specific nodes. And what they are doing is they're primarily responsible to bundling of transactions. They process and consume transactions from the parachain ecosystem, bundle them into something we call parablocks, parachain block, or maybe candidate alternatively, and they will be submitting those parablocks along the parachain protocol to backers. We'll get into that in a second. But the parablocks, because they're like aggregates of transactions, they transition the state of the parachain. They are just a parachain block transitioning the state transition function. And hopefully this image is familiar as well. It was what Sean was talking about. We have this parachain, the block of transaction provided by the collator, along with the Merkle proof of the state that will be used later on to validate a proof of validity. We'll go into details about that later on. But they're providing the block of transactions to the relay chain, to the backers. And so collators, once they actually build the parablock, once they aggregate all those transactions, they need to send it towards the relay chain. But who do they send it to? Like, we know that the validators in the backing groups, they rotate around every few blocks. So they need to send a message, a request to one of the validators to request, well, who are the validators responsible for my execution core? Who should I send my collation to? They send it to one of them, they receive a response. Okay, currently this specific backing group is responsible for your parachain. You're assigned to this execution core. And they send the collation to those specific backers. Question?
Question: Why are we why are we speaking in the terms of collection of transactions instead of just blocks? Like you're saying, like um, um, the nodes produce parachain blocks by collecting transactions together. I mean, I think it's obvious that like blocks are collecting transactions. So my question is like, is there another meaning to it here that we specifically say it, or?
No, it's a good point. Like, yes, a block is a collection of transactions.
Okay.
But what they are, I mean, there is a bit of a nuance to it. I'll get into it later on, because what they are providing is not just the block. They're also providing something called the proof of validity, which is like, think of it as an additional thing on the side of the block that helps you validate that the block is correct. We'll go into that later on.
Okay.
But yeah, you can think about it. They provide the block, the para block to be precise.
Okay.
And okay, so once they actually figure out like who is the backing group responsible for the execution core, responsible for the parachain right now, they just send those collations, those para blocks to those backers. And then we go into the backing stage. So we just send some collations, some candidates, some para blocks to the validators in our backing group. And what happens next? So the validators in the backing group, as I mentioned, are often called backers. For those specific parablocks that are coming in from collators. And those are the groups we created in the assignment step. So the few validators here are the first point of contact. Like the first validators here, the backers here, are the first point of contact for those parablocks, for those collations coming into the Polkadot network. Because those guys are actually validators of the Polkadot network from this 300 set of active validators. This was the outside world. We are actually coming into the inside world of Polkadot now. They're like the validators, you can think of them like club bouncers. They're like the first person you see when entering. But for them to do their job correctly, for the backers to do their job correctly, after receiving collations, they need to perform some checks. They need to actually ensure that what they receive is sensible. Because in the end, maybe they just receive random blobs from the collators. They need to do some checks on it. And to do those checks, we need to learn a bit more about the PVF. So the PVF, which is the parachain validation function, is just a complicated way of saying how does the validator verify that the state transition function is correct. So is that block correct? What they do in general is they get those transactions from that parablock, they get the previous state, they rerun the state transition function, just rerun the whole block and check the new state. And if the state actually matches to the promise that was given to from the collator, they can see, okay, sure, this is what they promised to us. And was it according to the state transition function? Was it a legal state transition? If yes, they give a true or false.
Can you please speak a bit louder? We're having trouble hearing you.
Okay.
Or closer to the mic, yeah.
Okay. The state transition function generally, I'm going to repeat the whole point just to make sure everyone got it because it's super, super important. Validators backers in that case have a list of transactions and they have the previous state. And they also have the state transition function, which is the WASM blob. This is the thing Sean was talking about. This is the magic instruction here of how to transition the state. And they simply rerun the whole block and see if it leads to a proper state transition, if it leads to a proper state at the end, and if it's the same state that was promised by the collators, because they also commit to that state. Question?
Yeah, Maciej, this function is run by validator or the collator? I mean,
Validator.
Then this was being done by collator previously, that they were generating the POV and submitting.
Collator is providing the list of transactions in the parablock, and validator is rerunning the state transition function to verify that those transactions are correct.
Okay, makes sense. And among so many collators, do they all submit to the backers, or one of them submit, or is there a consensus? What happens? Yeah.
Good question. So there's multiple collators. It's not only just 5, there can be many, many of them. And each of them can submit their own collation. And they all just send them to backers. Backers will have a choice which collations to choose, which collations to back. We'll get into that in a second, but generally speaking, they get a choice which one to select. But first, before they make the choice, they need to verify which one is correct so they can make an informed decision which to choose. And question behind it.
Thank
you. Just quickly, after this question, if you can just point to each component in this diagram and explain what it is. It's not very clear from the thing, but maybe after.
I mean, we'll be going through it step by step, but generally, the white dots around are collators. This pink square represents a specific parachain block. This is a backing group. The black square here is an execution core. The whole pink circle is the relay chain.
Okay, thanks.
But we'll be dissecting this whole infographic throughout the lecture. And you have some notes here as well. And validators, this is the backers. Backers are validators. Those two names in that specific case are exchangeable. They're backing the collations coming from collators. Yeah, and that's the same thing Sean was talking about. If we have the block of transactions, if we have the state, we rerun the state transition function and we get the new state and we verify if that state is correct. Question there.
So the collators themselves don't do the state transition function at all?
They often do the state transition function when they are creating the block.
Yes, and we're like it's like the backers do import the block to check whether it's hello.
Yeah, I can hear you.
There is and the backers do import the block to check the validity.
Good question. And they do check the validity, but I wouldn't say they do it specifically to check if it's correct. They will be actually, let me go to the next slide. The main reason why they're doing that is not to check if it's correct, but to have some accountability. They are the people that will say, I think it's correct or I think it's incorrect. So they do it to assign responsibility, to assign accountability. They will be the validators responsible for that candidate. So yeah, they do check if it's correct, but they do it to protect themselves. They do it so they don't by accident or by mistake say, oh, I think it's correct when it's actually not. So this is like the small nuance around checking.
And one more question. So these backers, is it an N that we a configuration that we say that for each parachain we have N backers, or how does it work?
It is a configuration, yes. The backing group size is a configuration. It's generally between 3 and 5. Right now in Polkadot it's 5. There are some ideas to lower it a bit.
Thank you.
Question here?
Is it correct to say that the collators have access to the parachain data, real data, and then they create the proofs, and then the backers only have access to the Merkle proofs and not the whole data structure in the parachain? Is it
Perfectly
like
correct, yes. Yeah. Backers only have access to the part of the parachain state that is given to them in the POV, which in itself contains the Merkle path you're referring to of the state necessary to do the state transition function. Okay. Hopefully that makes sense for everyone. If not, then raise your hand and we can go through it again. A question in the back.
What prevents the validator group assignment of colluding and validating a block that means some dots to themselves? Because the others don't validate the block, right?
You'll see in like 30 slides.
Okay.
We'll get there. But right now, what you're referring to is actually checking if it's truly correct. What we do right now is we just assign responsibility. We'll get to actually holding them accountable later on. For now, we just say, okay, you are responsible, and you'll go through the checks later on that actually in detail verify if you are truly correct or not.
Yeah, you're saying that they can be slashed if the block turns out to be invalid?
Maybe. That's in 40 slides. We'll get there. Like, yes, you are correct, but there's a lot of stuff to cover before we get to the final end result of you're getting slashed. For now, all we have is we have this guy that says, I believe it's correct, the backer, and he's responsible for that block. And we'll be going through the other steps now. Question there.
So, like more general question. You mentioned that the backing group is 3 to 5
Yes.
people, yeah? But in fact, in the beginning of the day, we allocate or choose 300 validators. And every 4 hours, this group just validate one parachain, right?
Every few blocks, if we have this backing group of 5 validators, they are stuck together for the 4 hours. But in those 4 hours, every few blocks, they get assigned to a different parachain, to a different execution core. So we are not constantly validating the same one. This is the
Alright.
rotations we're talking about.
But this group, if it's divided 300 by 6 parts, it's around 50 validators per 4 hours, right?
It's 300 validators chosen for the given 24 hours period,
Oh.
yes.
Okay, and how it happens that in one group there are only 5 validators?
We split them into subgroups. So we get this 300 and we divide it into multiple groups of 5.
Okay.
And then each group of 5 is each group of 5 in this image simplification 3 gets assigned to a specific execution core. So in reality, this ring is just significantly bigger. The groups are 5 and there's like multiple execution cores, not just like 6 of them.
Okay. And actually, it's just dictated by number of parachains, right?
Yes, the
Sure.
number of parachains is equivalent to the number of cores in that case,
Thank you.
and the number of backing groups. The backing groups number equal number of parachains equal number of execution cores.
So you said they are like randomly split into groups, right?
Yep.
And then rotated every so and so.
Yeah, every few blocks.
And they also get randomized, like regrouped.
Every 4 hours, they get
Every 4 hours.
re-randomized within those small groups. So
So-
you might land in a different group.
So to reiterate, like for any given 4 hours, there will be like a different organization of validators into groups, and in those 4 hours, each group would so they would rotate, like so they would do one block or a few blocks, and then another.
Yeah, it's like 2 free blocks on one execution core, and then you switch to the next one, 2 free blocks, switch to the next one, 2 free blocks, and after 4 hours, you get mixed with different validators, so you're in a
Yeah.
different group, and you repeat the whole thing again.
And you say 2-3 blocks. It can be 1 or a million. Like, is it?
It's parameterized. It's a specific number.
Okay.
So why I understand the number of parachains equals to the number of cores, but why equals to the number of groups? Each validator can have multiple cores, or am I not understanding correctly?
You are assigned to a specific group, to a specific execution core for a specific relay chain block. So why is it a one-to-one mapping? Because in the end, those parachain blocks will end up in the relay chain. And for a specific execution core, then can be one parablock going through. One parablock for execution core in the final relay chain block.
Okay, so it's one core per backers, like
It's one core per backing group.
backing
This is
group.
the backing group, and this is the core.
Sorry, maybe I'm missing. What is an execution core? Is this something that we will?
We'll have an in-depth lecture on execution cores
Okay.
by Bradley. Yeah,
Okay.
we'll go into that into a lot more detail, what it means for the execution cores. For now, all you need to know is execution core is just an abstraction that means that an execution core can compute, can have a scheduled a single parachain. It can compute a single parachain block per relay chain block. This is the ability of an execution core. It can execute a single parachain block per relay chain block. Okay, so the PVF, like this whole verification, in the end, it should give us 2 possible results, like the main 2 results. Either a transition was legal, it was valid, or it was invalid. If it was invalid, the backer is like, well, it's invalid. I will not be backing it. It's incorrect. I will not say it is correct because then I might be punished. Something bad might happen to me. I will take responsibility for an invalid block. But if it's valid, he says, okay, I can take responsibility for it. I believe it is correct. It is valid. Okay. So to give a small reiteration, we, as a backer, we receive the collation from the collators. We actually check if it's valid, and then we sign a statement on it. Like, it's a cryptographic system. Like, if we think something is valid, we need to sign a statement, an unrevocable statement proving that we believed at one point it was actually valid. And then we start distributing that statement with other backers in our backing group. So we mentioned there's like 5 backers in a single backing group. You start sending your opinion, your statement, do I think it's correct or incorrect, to the backers in your group. And after you get to a certain point, like this is inside of your backing group, you start circulating the statements for that specific candidate. And once we get enough approvals, so if we have 5 backers, right now in Polkadot, we require 3 out of 5 backers to agree that this candidate is correct. And if 3 out of 5 backers actually agree it's correct, only then we start broadcasting this specific candidate outside of the backing group. So the backing group is like this small council that is the initial check, the initial responsibility group for that candidate before it's being distributed to the whole network. And after it gets distributed to the whole network, we go into availability. There will be a whole lecture on availability, so we'll go through that, like the high level strokes of what it does. But at this point, the backers, they took responsibility. They have skin in the game. They say, I believe this block is valid. So they need to also make the data for this block available. Because if they say, oh, I think it's available, but the data it's no longer available, you guys cannot check it. Well, if they cannot check it, then they cannot be held accountable. They also need to start being responsible for making sure that the data needed to verify the block is available. So others at one point can also verify if it's correct or not. But the big problem is, like there is a naive way to do it. Every single validator in the whole system, so that the 300 validators just download the whole block. Everyone has it at their drive, then there is no issue then. But it's just not scalable. If everyone has to download the whole thing, each POV can be like up to a few, I think 5 or 10 megabytes. We have like tens of cores. Each block 6 seconds is a gigabytes per day, gigabytes like per hour. It's like a huge amount of data. It's totally not scalable. So we need to have some kind of data sharding. And data sharding, next lecture. But for now, I'll give a quick intro to it. This is a line. And on that line, we have 2 points. This is a first degree polynomial. We can have a second degree polynomial with 3 points. And the interesting thing is, if you have a line, if you have just those 2 points, by even not knowing the line, you can obviously say what is the line that goes through those 2 points. And it goes further if you have a quadratic. This is the second degree. If you have 3 points, you can always exactly say what is the quadratic that goes through those 3 points. If you have a third degree polynomial, if you have 4 points, you can always exactly tell what is the curve that goes through those points. And hopefully you start seeing a pattern here. But if we have 3 points on the same line, well then, even if we, for some reason, forget one of the points, it's no longer available to us, well, we still have enough to reconstruct the line. If the line is what we care about, then maybe we lose that point. Well, we still have the line. Maybe we lose that point. Well, we can still recreate this line. And this is like the core idea of erasure coding. But if we lose 2 points, then we are kind of screwed in that case, because, well, there's many different lines that can go through this one individual point. We can no longer recreate our line. So we have to be very careful. There is a specific threshold of how many points we need. And on a high level, like we use this idea in erasure coding for our data availability. We simply get the data we need and represent it as a very, very high degree polynomial. It's just a very curvy curve. We just encode our data into this curve. And we get a bunch of points on that curve, and we give every single validator in our set, so the 300 validators, each of them gets a single point. And we have enough of those points there that we only require 2/3 of the points to reconstruct the curve. So even if some people do not cooperate, some of them lose their points, they lose their availability chunks, we can still recreate the data. We have redundancy. We have redundancy, but at the same time, not everyone has the same thing. So it's the best of both worlds.
I feel like I don't see the how we skipped from like the state transition function and the blocks and the Merkle roots
Mhm.
now into like polynomials and data, like well, data, yeah, but like how, because they are validating a block, right? So it's a single data point, really, like before and after, right?
This thing here can be like 5 megs.
Sorry?
This thing here can be like 5 megabytes.
Yeah.
It's a lot.
Yeah.
If you have like 60 cores, each one pushing this thing every 6 seconds,
Yeah.
and you need to store it for like 24 hours, it's going to be a bunch of gigabytes every while. And it's simply not scalable for Polkadot nodes to always download and store this amount of data for a huge long ass time.
Okay.
So we need to somehow make it so nodes can store less data.
Yeah.
And not only less data, but if for some reason one of the nodes doesn't cooperate and says, oh, I will not give you my data, then we are not screwed. So we need to have some data redundancy. This is one point, but at the same time, have less things to store. And this is where erasure coding helps us. It gives us data redundancy. We only need some of the points from this very high degree curve to reconstruct the curve. But having a single point is much simpler than having the whole curve stored because it's much less data.
Sure, but it's just how do we then okay, maybe it's my math ignorance here, but like
Go on.
how do we like map the data into a polynomial?
Very good question. Today there will be a lecture and
Okay.
Bradley will be doing that in detail, actually showing the Lagrangian transformation to how to do it. It's a lot of maps. It's a very lovely lot of maps, but it's a lot.
Okay.
For now, you just have to kind of trust there is a way to map the data into a very high degree polynomial.
Okay, and then the yeah, okay.
Cool. But yeah, it's a good question. It's a very interesting topic, and we'll be going a bit deeper into that. Okay, and because once we actually distribute all those availability chunks, all those points on this very curvy line, we have people sign a statement saying, okay, I received my point, I received my chunk of the data. And once enough people start saying, okay, I have my chunk, once 2/3 of the network say, I have my chunk, it means that we at this point can recover the data because we need 2/3 of the chunks to actually reconstruct the data. So this is a specific threshold at which we say that this data becomes available. It can be included, it can become available, it can be reconstructed to actually verify it. So we can proceed to the later stages once we achieve availability.
Just for sake of memory, the 2/3 thing comes from a proof, which is like this.
It's a parameter.
The theorem. What?
It's a parameter.
Yeah, no, but
2/3,
we could the faith in this 2/3 figure comes from some theorem, some math theorem, something about, I don't know, but we had it in a previous lecture. I don't
Okay,
remember.
so the 2/3 in that specific case could be a different number. We can parameterize it to be something totally else. The reason why we chosen 2/3 is because our finality gadget grandpa assumes that 2/3 of validators are honest. And we simply wanted to have a similar, the same threshold as we assume in grandpa. Because generally in Polkadot, we assume that 2/3 are honest.
Okay.
But it's coming from grandpa.
But I think I'm just saying, I think that comes from a backing like theorem about data that it was mentioned in the previous lectures. I don't remember what it was.
It comes from grandpa. Grandpa is the main thing that creates this assumption of 2/3 honest.
Okay, I think there's the grandpa. Again? Yeah, maybe.
Yeah, but the Byzantine fault tolerance come from our grandpa assumption, which lock it to 2/3.
Okay.
Because then if we have more than 2/3, if we more than 1/3 dishonest, then our Byzantine threshold is crossed and our consensus breaks. It's just different names for the same thing. Okay, so once we actually have the 2/3 available, 2/3 of the chunks in validators, we can say that this thing is available, it can be included. And there's a bit of a difference between inclusion and finality. Just because it's included in a relay chain block, it doesn't mean it's final yet. Like, it is there, but it's not final. And the main important things is that only valid blocks can be finalized. And now we have to start working on ensuring that this whole thing is correct. We finished setting up the stage. We have the data available, and now we can actually go to this idea, oh, but what if they're colluding? What if this is just wrong and invalid? We'll be working on making sure that all of that is correct. And for that, there's this whole huge system of approval checking. And before we go to it, question.
Really quick, how does the recovery process work? Is it like a DHT that holds particular chunks?
Good question. I will not go deeper into that because we have a full lecture on that.
Sure.
So
okay.
just a waste of time. But yeah, it will be answered. And if it won't be
Sure.
answered, then ask in that lecture.
Will do. Thanks.
Cool. Okay, approval checking. So approval checking is, in my opinion, the most important part of the protocol. And it's also the biggest chunk of the work. Like, this takes a huge amount of compute and execute. And you can think of it as like this battle royale of candidates. Like, this is the moment they will be actually deemed worthy, deemed correct or not. And only those that do survive the approval checking will be able to get finalized. So what even is validating a parablock? We already touched upon it, but just to make sure we go through it again. So now that we have the data available, we need to work on recovering the data. We'll go into details of how it works exactly later on, but you start fetching all the chunks for that specific parablock you're trying to validate. And once you have this data, once you have the necessary data of the parablock, the transactions and the state, you can start executing the PVF. You can just re-execute the whole block, checking if it's successful. And if it is successful and it matches to the commitment of the state of the backers, because the backers took responsibility for that, you need to verify that this is the same block as the backers were responsible for. And only then we can actually start sharing our decision. Is it correct or is it incorrect? And we'll be sharing the decision with the other validators. But before we go into it, the important note is that the approval checking process is started whenever any block is included. So for every single included block, there will be this approval checking process kickstarted. And every single validator in the whole system, so the 300 validators, will participate in approval checking. And we'll go into details of how it still preserves sharding and does not take too much compute. But to see how it works is, first imagine you use the VRF to randomize a number. You just do it a secret randomization between a 0 and 100. And this number will generally be used to show how much delayed should your check be. If you roll a number 0, you'll be performing the check super, super early. If you roll a number like 100, you'll be doing the check super, super late. And others don't know the number you get. We use the VRF, so it stays secret, but if at any point you need to prove what number you had, it's still possible. And the people starting with the lowest randomized numbers will be saying that they are in the lowest tranche of checkers. They're doing the first people that actually do the checks. And a good way to visualize it is, for instance, we have the first group, people that have the numbers between 0 and 10. I'll get into why the first one is a bit bigger in a second. And then everyone that rolled an 11 in the VRF is like in tranche 1. Everyone that rolled a 12 is in tranche 2. And it's randomized. It doesn't always mean that there will be this exact amount in that specific tranche, but we can statistically expect that there will be some people in every single tranche. And the people in the later tranches will start doing the checks after a certain amount of time. Imagine that the tranche 0, once the inclusion happens, they immediately start recovering the block. They get the data, they run the validation, and they start publishing their results. But the people in tranche 1, they wait for a few seconds. People in tranche 4, they wait for even more seconds. People in tranche, I don't know, 25, they will wait for even more time. And this is crucial because we don't want everyone to do the checks. Like, this is our goal. If everyone does the check, we don't scale. But the important thing is we don't require everyone to do the checks. We only need a certain subset of people to say, oh, I believe it is correct. So in Polkadot, the way it's parameterized is we require 30 approval checkers to say this is correct. And 30 approval checkers is generally the size of the tranche 0. It's on average that size. So usually most checks are happening like that. We have the inclusion. The first tranche is the people that rolled really, really low numbers, should be on average 30 people. Those people start recovering the data. They start checking. And if the block is actually correct, then they start submitting to other validators. Well, I think it's correct. Once the other people start seeing that we have 30 confirmation that it is actually correct, the later tranches no longer have to participate. They see, oh, we actually reached 30 early. We no longer have to do those checks. Our help was not needed for that specific candidate. And this saves us on the compute in the happy path, because it's so many people already approved that at this point we no longer have to commit resources to making sure it's safer and safer. It's just safe enough. And interesting point is that, well, what if like all of those 30 people, the 31st people in the tranches, what if they're like all malicious? It sounds like an issue, but the chances that all of them are malicious is like, I think I have a note on that. It's like 1 in 200 trillions. Assuming that only 1/3 of the whole validator set, so 300 validators, assuming that 100 of them is malicious, the chance that all of those 30 are malicious is like 1 in 200 trillion. It just doesn't really happen. Statistically, it's pretty much improbable. Because if there's at least one honest guy, he can start an escalation process. And we'll get to that in a second. And there's also this extra bit of information here, because there's something we are very, very afraid of. We are very afraid of that if a single validator, malicious attackers, if they in the end want to have 30 confirmations that say, oh, I believe this block is correct, that they can start DOSing honest validators in this protocol. So we don't want to leak information into who is actually assigned to which tranche, because then they would know who they should DOS. And the way it's handled is, if you are in a low tranche, instead of saying, oh yeah, I'm in the lowest tranche, you just say, I'll be doing the checks now, but I don't have the result yet. Because then you need to start downloading, you need to start fetching the data. And fetching the data announces yourself as someone that does the check. And this is a moment where they could be DOSed. The attackers can see, oh, this guy is fetching the data. If he's fetching the data, if we DOS him and he cannot actually publish the result of his verification, then we can silence him. And this is a very, very risky situation, because if you silence him and you only left the malicious guys remain, then getting 30 confirmations is possible. So we have to be very cautious around that. And if someone says that I will be doing a validation and they start fetching the chunks, but they suddenly disappear, we call it a no-show. It's someone that said they will be doing something, but they suddenly do not show up for the result. They disappear. And for that, we have to be super, super cautious. And what we do is, if, for instance, in tranche 1, everyone said, I'm doing the checks, and everyone did the checks. But then we required a bit more checks. Maybe we had only 28 people in tranche 0. It's statistical, so it can happen. Then we go into tranche 1. And in tranche 1, there is someone here that says, I'll be doing the checks, but then they suddenly disappear. Then maybe they were DOSed. What we do is we simply require more people to do the checks. We slightly escalate the issue. We add one extra tranche on top of the checks. And until we get the original amount, the original 30, plus one extra tranche, we are not satisfied. And if suddenly in the next tranche, the same thing would happen. They would like DOS one of the guys. We add another tranche on top of that. And we just keep going and going until we get enough checks for every single person that was for some reason lost, some reason disappeared. And the idea behind it is that like this thing should be a hydra. If you cut one honest validator away, if you remove one head of the hydra, it regrows 3 new heads. There shouldn't be a way to just simply DOS them. We have to be stronger for every single missing validator. So in general, the important property is that because, actually, let's go to the tranches. Because we have all those tranches, for that specific candidate, every single validator of those 300 is assigned to do the checks at one point. But not all of them will do the checks. Only some of them will do. But everyone is technically assigned to do them at one point. And the general good property of that system is that either you had the assignment, this includes like when you should do the check, there is a very high probability you will simply do nothing because you were not even needed. Your number was so high that there was no need for you to perform the checks. In case that your number was pretty low and you are necessary, then you will reveal your assignment. You will say, hey, I'll be doing the checks. You'll get the data, you'll do the checks, and there are only 2 options. You either say, I believe it's valid, or I believe it's invalid. If you believe it's valid, that's the happy path, the good path. You simply start distributing a statement saying, I believe this block is correct. And once we get 30, it passes. But if it's invalid, this is pretty bad. And we start the very strong escalation. We initiate a dispute. And dispute is the next subsystem we'll be going into. Like what happens if not only someone was DOSed and we just need to add more people, but something was found invalid and we need to fully escalate.
Can you go back one slide, please? Yeah. So the validators at this stage, they are still like the groups, or like are they everyone? Because now we're doing the relay chain.
All of that happens in parallel. They might be doing that thing for one of the candidates while they might be backing a different candidate. So this is a totally separate subsystem. Like every candidate that goes through this scheme here at one point was backed. It doesn't mean that they were backed by the same people doing that. It's just a different subsystem later down the stack.
Yeah, but so they might be part of like a backing group, right?
Every validator is always a part of some backing group,
Okay,
yes.
so they are a part of backing group, but now
maybe not for this candidate, maybe for a different one.
Sorry?
They might be a backer for a different candidate, not necessarily for the one going through approval checking here. This candidate was probably backed by someone else.
Okay, so now we're still in the process of like, so now is the approval of still like a parablock, right?
Yes.
But in order to integrate it into the relay block, right?
Yes.
And so the trenches, what do they represent? We don't have the slide, by the way.
You don't have the slide? Okay, I'll update later on. These tranches, they represent how much you should be delayed in doing your checks. So the people in tranche 0, they start doing their checks immediately. People in tranche 4 will wait for some specific amount, I don't know, like 4 seconds before they do their checks. But if before those 4 seconds actually go, we already have enough votes, we already have enough checks that they don't even happen. It's just how much you should be delayed in your checks.
So, but in a sense, like every tranche includes a number of validators.
Yes, every tranche is on average between 2 and 3 validators. Statistically, it can be, it's random.
2 and 3.
Yes.
But the first one, no.
The first one is a bit special, and the first one is big. And the reason why the first one is big is actually pretty simple, because we require 30 checks.
Yeah.
So there is no reason to delay the first few groups because we know we need more. So the first one is just specifically made bigger to, on average, account for the average amount of checks
like
we need.
In the good case, like in the optimal case, only tranche 0 would
Exactly. Like
okay.
in most cases, only tranche 0 is needed.
Okay. And again, like each validator would randomly appear in any of them.
Yes, they roll the secret dice, the secret VRF, and only they know in which tranche they are.
Okay.
Cool. Any extra questions?
So you mentioned statistics of the malicious possibility of malicious like validator, right?
Yep.
But it could be coordinated attack, right? So it's like
Could be.
it's if it's like intentional coordinated attack, it could be much more.
Not necessarily.
How it
So
works.
even if you're coordinating, like at most we assume that you have 1/3 of the network malicious, which is 100 validators. So the chance that the first 30 are all malicious is the 1 in 200 trillion. It's just like it's very likely that there will be some malicious guys, but just having a single honest guy is enough to escalate. It's enough to, if there is a single honest guy, it's enough to, you see your assignment, you reveal your assignment, you do the check, and they cannot silence you, because if they silence you, we just add another tranche, so it doesn't help. So you need to make your check, but if it's actually incorrect, if you see that this block was invalid, then you will raise an alarm, you will escalate, and you initiate a dispute. And we'll go into what a dispute is in a second, but this is the biggest escalation that can happen in Polkadot.
Okay, and approval checking happens after the backing group.
Yes.
Check, yeah?
Initially, collators produce the block, backers back the block, inclusion, availability makes the block available, and then approval checking.
Okay. Thank you.
Cool. Question behind.
So can you get to the first approval checking slide? Yes. Because we have different slides.
I mean, the first one, I guess, that.
Yes. So the approval checking is the validators, whether backers or not, right? Getting the
Every validator is a backer as well for some
yes,
core.
yeah, and they are validating the new block that they get, that it is true, right? Making what's written in the second point, executing the para block using PVF. The proof-
Parachain validation function. This is the how do they actually know if it's correct or not. This is the function that gives them it's correct or it's incorrect by rerunning the block.
Rerunning the block.
Yes.
Rerunning the state transition function again.
Correct.
So the collators do run the state transition function, and then the backers do run the test.
Collators do it, then the backers do it, and the approval checkers do it, and if there's a dispute, then they also do it. Yes. If at any point you need to say, is it correct or incorrect, it means you're rerunning the block.
Okay. And the part of the recovering data from the network, this is the availability with the erosion.
Exactly. This is the
will
downloading the chunks from other people so we can reconstruct the data. You can fetch the chunks, you can have this huge polynomial, you transform the polynomial into the data you need, and then you can use this data to check if it's correct.
So each data will get 2/3 of the chunks needed and then rebuild the last third?
To rebuild the data, you need 2/3 of the chunks correct.
Okay, thank you.
There are some optimizations around that, and I think they will be mentioned in the availability section because there's a lot of optimizing around that, but this is the broad strokes. We good? Good. Okay, escalation. So if one of the approval checkers does their job and actually sees, well, this is incorrect, something is wrong, this is a huge problem and it needs to be heavily, heavily escalated. So they raise an alarm, they shout to everyone, there's an issue, there's a dispute, we need to actually come here and check this out. And overall, the whole idea behind Polkadot is attacking the network is possible, but it's just very costly. And we need to build it in such a way that it's just not sensible to attack the network, the gambler's ruin. Like you can win at one point, but it will cost you so much, you will go bankrupt before you can achieve anything. So an attacker that can go through the approval checking process like this 200 trillion times, well, at one point, he will succeed and get the proper 30 malicious guys at first in the tranche 0, but it's not probabilistically sensible to go through it. And now we need to limit the amount of tries he has. So every try he actually attempts and fails, he needs to pay for it, and he needs to pay for it a lot, so that he goes actually bankrupt before he can repeat that, well, 200 trillion times. So when two validators disagree about the validity of the parablock, so one of them says correct, the other one says incorrect, it raises a dispute. There's a discussion like, is it correct or not? And disputes, because they're a form of an escalation, they involve all the validators. Once you initiate a dispute, it goes to every single validator. We ignore the tranches. The tranches are no longer relevant. The message goes to every single one from the 300, and all of them do the PVF checks. All of them recover the data, all of them run the checks, and all of them say, do I think it's correct or incorrect? And because it involves everyone, it's very costly, but it gives us the ultimate source of truth because, well, we have the assumption that only 1/3 is malicious. And for disputes, we'll actually get to it in a second. One extra point. So I said it's very expensive. So disputes, they break sharding. If we do a dispute, if we find a problem, for a second, we no longer have sharding. Everyone does the work. But this is this moment where we can sacrifice sharding for ultimate security. Like it's only temporarily to actually punish, to find the attacker and punish him. And if everyone is doing the checks, and we know that only 1/3 is malicious, then if we have a supermajority, a 2/3 people saying it's correct or incorrect, we can trust them. A supermajority in our system is trustworthy. They always bring out the truth. So once the dispute has 2/3 opinions one way, we say, okay, it's resolved. This is the final conclusion. The block was valid or invalid. And if the block was valid or invalid, there was someone on the other side. Because remember, the dispute only starts if we have two validators disagreeing. And this person that is on the incorrect side of the dispute, they need to pay for it. And they need to pay a lot. Generally, if they are a backer, the backer that was responsible for that block, if it is found to be invalid, is slashed 100%. They lose all the stake, everything. In cases...
So just quick question, sorry for interrupting. What about those who actually backed like the side which is wrong in the dispute? Are they also punished?
So the backer, so the original people that were assigned responsibility, so the group of 5 potential people, they get slashed 100%. They lose everything. But there might be some people that were not the backers, but they took a wrong side in the dispute. We actively update the system, and this is like my main area of work actually. Currently, we don't have to slash them that much. We only do some disabling, and it's another thing will not be covered here. I can talk with you that after the lecture. So we limit their privileges a tiny bit to ensure they cannot further attack the network if we assume that they did some malicious activity and they voted incorrectly. But we don't have to slash them that much because someone already bears the responsibility. We already slashed probably between 3 and 5 backers 100%. This is already millions of dots. It's if they're colluding with those attackers, they already lost so much money, then slashing a few extra percentages like those guys on the side just doesn't matter. It's not relevant. We only need to make sure that there's at least one person that pays heavily for it, that was really, really responsible. And as we established at the beginning, the person that bears the responsibility, that is accountable, is the backer. They said at the beginning, I take responsibility for that block, and they will pay for it if it's incorrect.
Okay, thank you. And could you also please comment as how costly it is, how expensive this dispute resolution is?
I mean, for a single dispute, it's not that bad because normally we have the average of the 30-something checks if on the happy path in the approval checking. Dispute is just the same time, it's everyone checking, so it's 10 times that. So it's the cost of 10 normal approval checking procedures. If there is a single dispute, not an issue at all. But if for some reason there's like, 1,000 of disputes, it gets expensive. It just breaks sharding. For a second, everyone has to do everything, question in the back. And then here.
So realistically, up until now, how often do they happen?
Disputes?
Yes.
Pretty much never. It's a very, very, very good question, because disputes is like the main thing I'm working on. And it's super funny because we write this code and we design this system in such a way that it hopefully never ever executes, because it needs to be run. It needs to be so perfect that no one even wants to attack it, because they know if the disputes happen, they are screwed. But the whole idea is they shouldn't happen, but they are there to prevent you from even attempting. To be fair, they do happen sometimes, usually because a few things. Either there was some weird bug and a validator backed an incorrect block, or an incorrect block was produced, there's something weird happening. If something that exceptional happens and you can prove it was a bug, go to governance, you open a referendum, you prove that it was a bug, and you will get refunded if you were slashed. This is why governance is good. Governance helps us manage exceptions, that where you can prove it was an exception. Yeah, but attacks generally don't really happen. But they might happen in the future, so we need to have this system.
Yeah, my idea was the same what he said, but in a different word, I'll say the assumption of Byzantine fault tolerance system, that if 2/3 of them are backing, then we don't have to care about the remaining 1/3, whether they are saying correct or incorrect. So once we achieve the majority, 2/3 are saying it is correct. Is it really, I mean, yeah, we have the dispute, even one dispute, we are taking it so seriously, that is good. But is it really necessary? I mean, once we have achieved majority that it is true.
I mean, once we have to...
super majority that the block execution was correct. Now only one dispute comes. Even the majority is there, but still because of one dispute, it will be escalated very heavily. Maybe because of the bug that was reported, as you said, the node will have to go through the governance, recover and all, recover the fund, which was slashed because of his bug or something.
Yes, but where is the question? Or
the question is, if majority says that the block execution was correct, do we really have to escalate if one?
Yeah, but we only know that the majority says it's correct because we escalated. Like, the escalation causes everyone to check. So before we escalate, we only get like the 30-something people checking, so we don't have a supermajority. We only resort to the supermajority if we really have to in the escalation process, because it's very expensive to get a supermajority to show up.
Got it. That time it was only 30. I thought, I was assuming that's kind of majority. Yeah, thank you.
Makes sense?
Got it.
Good. Okay, nearly done. Yeah, so this is the slashing aspect I was referring to. The backers are paying 100%. All their nominators, everything is getting fully slashed. They are bearing the full responsibility for backing something that was invalid. So that's why the backers were doing the checks initially. They were not done for security. They are protecting themselves, because if they don't do it, they will just get slashed. So they need to do it for themselves. So, okay. Now we went through most of the protocols. We went through collation, where you actually create the parablocks. We went through backing, where some people do the initial checks, assign responsibility, availability, which gives us the data so other people can do the checks, and then actually verifying if it's correct or not. And if it's incorrect, we escalate into disputes so we can actually punish the attackers. And this is the core of the parachain protocol. And the small mini extra thing is block protection. Once we actually go through this whole thing, we can start adding stuff into the relay chain. So we have this thing called Babe. I think most of you heard about it already, which selects us an outer. This outer selects from those blocks the ones that were available. He includes them, and then all those blocks, they will go through this approval checking process to verify if this whole block, if all the para blocks in that relay chain block are actually valid or not. If every single para block in the relay chain block is valid, only then the whole relay chain is also valid. And if not, disputes happening, people getting slashed, people getting punished. And the thing that actually ends up in the relay chain block is a candidate receipt. So a lot of extra stuff, but the main thing is the thing that ends up in the relay chain block doesn't have all the data of the parablock. It doesn't have all the transactions. It is just a commitment to that specific parablock. It has like a state root of this parablock. It has a hash of the block, and it has a root of all the outgoing messages. That will be the XCM stuff we'll be covering later this week. So it's just a bunch of commitments to the data there. And we'll be having the Babe being upgraded to Sassafras very, very soon. A few nice things about it is simply Babe is nice, but Babe only works in like 35% of cases. So in the rest of the cases, we simply have Aura, which is the round robin block offering. Generally speaking, that is enough to give us some randomness, some good on-chain randomness, but Sassafras will make this percentage of block offers being generated from Sassafras instead of Aura significantly higher. It will also reduce the amount of forks we have, because Babe, sometimes you can have 2 people be the authors. It's not a security risk at all, but it's simply something we need to resolve later on, and it's just wasted effort. If multiple people author blocks, then it's more validation, more approval checking, more everything we need to do, and Sassafras helps us reduce this amount of wasted effort. And the authoring mechanism is also paired with a chain selection logic. In Bitcoin, you're probably aware, just select the longest chain. In our system, it's very, very similar. But what we do is we can leverage this idea of forking to tactically ignore forks that have blocks that lost a dispute. So if we have some candidate, we had a dispute and we know it's invalid, then the fork choice rule will simply say, ignore this block, build around it, build another fork next to it so we can totally go around and reorg it out. So the forks are coming to the rescue here. We can simply ignore the information that doesn't suit us, that was proven to be incorrect. And technically, we could depend on probabilistic finality, just like Bitcoin, just assume that at one point, once we have enough blocks, this is final. This is not ideal. It takes a long time to be fully sure. It's never fully sure. It's just like 99.9999%. We want something precise. We want something that at one point, we know this is finalized for 100%. And it was also introduced, but that's why we have the Grandpa module. It allows us to do some extra layer of voting that with a bit of extra effort gives us a confirmation. This is final. Like everyone agrees 100% that this is final. And it's pretty quick. We don't get the finality after minutes or days or something. It's under like, on average, I think it's like 20, 30 seconds or something. Yeah, and as I said before, instead of voting on the longest chain, they simply vote on the longest chain where all the unfinalized blocks, the one we are voting, are either approved in the approval checking process and are not currently disputed, or they are not already proven to be incorrect. So this is the longest correct chain. Pretty simple in the end. And some super extra notes about the nitty-gritty details of how it's actually implemented, if any of you will be looking into the code base, but a very, very, very short summary. As you know, we have the node and the runtime. And the runtime is updated by the new blocks. Malicious or poorly connected validators could have some choice in which information to provide to the runtime, but hopefully in the end, all of that will be sorted out in the approval checking process. And generally, we have the runtime APIs providing us the information from the runtime. The big thing I want you to also be aware of is we use something called orchestra, and this is simply an subsystem orchestration tool that helps us synchronize all those different subsystems like collation, backing, availability, because they all run in parallel, which is not that easy to do. And they all send a bunch of messages around. So we need an orchestration tool that helps us actually manage the traffic between the subsystem and manage there is no race condition, because a race condition in blockchain would be terrible. We need to be deterministic. Something like that cannot happen. So we have a bunch of signals passing around, a bunch of heartbeat that protects us from race conditions. And And we have a bunch of different subsystems, as I mentioned. They don't map exactly one-to-one to the 5 sections we had today, but we have a dedicated dispute participation subsystem. We also have a dispute coordinator. So sometimes there are multiple subsystems for each section we covered today, but overall, it just covers the same responsibilities that we were talking about today, just subdivides them a tiny bit more. We have the candidate backing. We have the availability distribution that does all the conversion to the curves and distributing of the chunks. We have the approval checking, which does the assignment of tranches and the checks. We have the collator protocol, which actually creates the para block and introduces them, and a bunch of other ones because there's a lot of them. And all of that is generally explained in the implementer's guide. There will be a link to that guide, I think, in the notes, or it was in one of the first few slides, which is the go-to gospel book of how the parachains protocol work. All those different subsystems today, they should be roughly explained in that guide. Any extra questions at the end? Because there's a lot of content. I'll be around here for the rest of the week if anyone wants to chat about any of those systems. There will also be extra lectures covering data availability, execution cores, some extra details around async backing, which is an optimization for backing, and other extra stuff. Because this is the basic, the bare bones of how the system operates. There's a lot of extra stuff on top to optimize it.
I have a question. I just want to confirm that at any point, every validator has wasm blob of every parachain, right?
Correct.
So
It's stored in the state of the relay chain, yeah.
okay, so if the validator is assigned to the back group of any parachain, it just retrieve the blob, the wasm blob, and do the validation, right?
Yeah, exactly. The blob is not provided in the POV because the validators in the relay chain already should have the blobs. They maintain those.
Okay.
And they can get updated over time if there is a blob like a forecast upgrade. Any extra questions, or are we done? Cool. That's all.